Welcome to This Explainer. Okay, today we are going to dive straight into the gritty reality of modern product development. We're going to look at exactly how engineers are ditching physical prototypes for digital simulation. If you've ever wondered how on earth aerospace components or, incredibly complex consumer electronics actually get tested before a single physical part is ever manufactured, well, you are in the right place. We're tracking the evolution of computer-aided engineering and how it's radically transforming the way we design the physical world around us. So let's start with a quick baseline definition. Computer-aided engineering, or CAE, is basically the ultimate problem solver. It's the application of computational methods to evaluate how designs behave under real-world physical forces. We're talking stress, heat, vibration, fluid flow. It allows teams to predict exactly how a part is going to perform in the real world without needing to build a costly, time-consuming physical prototype first. You are effectively testing reality, but entirely inside a computer. And the return on investment here, it is absolutely massive. Just as an example, look at CAE plastic industry. By using CFE to run injection molding simulations and flow analyses, they were able to visually confirm their mold accuracy before any manufacturing actually started. This digital testing allowed them to reduce their physical trial injection runs by a full 25%. That is a massive saving in both time and material costs, going straight to the bottom line, simply by simulating the physics beforehand.
All right, here's our quick roadmap for this explainer. 1. The power of CAE. 2. Fixing the geometry bottleneck. 3. A platform showdown between SimScale and ANSYS. And 4. The AI engineering revolution.
Okay, section 1, the power of CAE. Let's get into it. Now, CAE isn't just one monolithic thing, It actually encompasses several different physical disciplines. You've got finite element analysis, or FEA, which is used for testing structural integrity, so checking stress, strain, and deformation under tension or compression. Then you've got computational fluid dynamics, CFD, which is absolutely vital for analyzing complex aerodynamics and fluid flows. We also have multi-body dynamics to evaluate motion forces between connected components, and thermal analysis to predict temperature distribution. These are the core pillars that basically ensure a product won't fail when it finally meets the real world. Moving on to section 2, fixing the geometry bottleneck. So here is the gritty reality of simulation. Before you can run all those amazing complex physics calculations, you have to prepare the messy real-world CAD files. You almost never get a perfectly clean model from a design team, right? We can generally break this preparation down into 3 main steps: finding and fixing overlapping parts, extracting the fluid volume, and wrapping the surface. Step 1, interference detection. This is absolutely crucial. Imagine you have 2 parts fighting for the exact same physical space in your file. If you don't detect and fix these overlapping solid parts, they will completely crash your simulation setup and cause your meshing algorithms to just fail outright. The software literally cannot calculate the physics if the geometry is physically impossible. But what if the automatic interference fixes fail? Well, then engineers have to roll up their sleeves and use manual Boolean operations. This gives you really granular control over your geometry. You can union overlapping entities to merge them into a single volume. You can intercept them to create a brand new entity out of just the common volume. Or you can subtract them. The cool nuance here is that when subtracting, you can choose to keep tools to remove the common volume from your target only, or discard tools to remove both the common volume and the tool body entirely. Now, beyond overlapping parts, you might also just need to delete unnecessary faces to simplify the model. Think about removing totally irrelevant details, like the threads on a bolt that are just going to waste computing power. When you delete a face, you utilize healing methods. You can heal the gap, which expands or contracts the adjacent faces until they finally intersect. You can cap it, connecting adjacent faces without changing their original shapes. Or you can simply leave open, which leaves a void and turns the solid into a sheet body. Okay, once your solid bodies are squeaky clean, we hit step 2. If you're running a CFD simulation, you need to extract the flow volume. This is literally generating a brand new 3D shape out of thin air, or, fluid, that represents the air or liquid around or inside the CAD model. To do this for an internal flow, say water running through a pipe, you define a seed face on the inside and specify your boundary faces. The software then builds the fluid domain that the physics will actually act upon. And finally, step 3. For CAD models with overwhelming artifacts like crazy self-intersections, cracks, or just extreme complexity where cleanup is basically impossible, that's where the Wrap Surface tool comes in. It creates a simplified, meshing-ready envelope around your entire model. You've got precise settings here. You can choose a really stable fit to surface or snap to edges to preserve sharp angles greater than 30 degrees. You can also tell the algorithm to allow complex tunnels or automatically cap tunnels to close off annoying little pockets and gaps. It's essentially a digital shrink wrap to save your simulation. Section 3, Platform Showdown, SimScale versus ANSYS. Zooming out to the macro software landscape, and based on data from RFP Wiki, we're seeing a massive shift happening right now. On one side of the ring, you have SimScale, which pushes a highly accessible cloud-native philosophy. It's browser-based software as a service designed specifically to remove the need for local high-performance computing hardware. On the other side, you have ANSYS, representing the deep, legacy, industry-standard approach. ANSYS provides a deeply comprehensive multi-physics platform that's traditionally anchored to the desktop, though they are definitely pushing into hybrid cloud solutions. Looking at the hard numbers, SimScale definitely wins on ease of use, with a very modern UI and 100% browser deployment that shatters hardware barriers. ANSYS, however, maintains the lead with a slightly higher overall score of 4.6, largely because of its sheer physics depth. While SimScale offers a really broad range of CFD, FEA, and electromagnetics, ANSYS is the heavyweight champion for highly complex multi-physics, stuff like advanced explicit dynamics, crash testing, and layered composite materials. And the purchasing and support experiences? Yeah, they differ wildly too. Buyers consistently praise SimScale's transparent SaaS pricing and their live chat and video support. Conversely, ANSYS buyers often face real procurement pain points with complex token and concurrent licensing models, and sometimes report pretty slow resolution times for licensing issues. That said, when it comes to the technical weeds like meshing, ANSYS gives you superior fine-grained manual hex and boundary layer control, whereas SimScale leans much more into automated workflows like the Lattice-Boltzmann method. Which brings us to our final section, Section 4, the AI engineering revolution. So both that new cloud accessibility and the deep desktop physics are currently colliding head-on with, you guessed it, artificial intelligence. The future of computer-aided engineering is undeniably AI-driven. We are seeing machine learning integrated directly into these platforms. By utilizing physics AI and surrogate models, teams no longer have to wait hours for a traditional solver to grind through a single iteration. Instead, algorithms allow engineers to evaluate entire design spaces and predict performance in seconds, drastically narrowing down the options before they ever hit go on a full-fidelity validation. To really grasp the magnitude of this shift, you've got to hear this quote from Armin Narimanzada, a manager over at Convion. He says, "The design was complex, and using traditional simulation-driven optimization would have taken months. We now have an AI model that can generate a new optimized design in under an hour." I mean, that perfectly captures the moment we're in right now. AI is compressing optimization cycles from months down to a single hour. That is just an unbelievable leap in productivity. But AI's impact isn't just about creating faster solvers. It's the whole shebang. It accelerates early design iteration. It uses generative design to automate complex geometry creation. It integrates real-time IoT data for adaptive, living designs. It even automates the heavy lifting of orchestration and can actually generate proposal-ready technical reports for you. It's literally taking the busy work right out of the engineering process. Which leaves us with a pretty massive final thought to ponder as we wrap up this explainer. As these software tools rapidly evolve from being mere calculators into actual autonomous agents, are you ready for agentic workflow automation? How will these AI models, acting as autonomous engineering assistants, redefine your own role in the product design process? It's a wild, fascinating time to be in engineering, and these tools are only getting smarter by the minute. Thanks so much for joining me on this explainer, and keep exploring.